So today we've got a young couple that is madly in love with each other, Pat and Chris. And they're trying to decide what to do this Saturday night. The Russian ballet is in town, first time they've ever been to town, and the Ultimate Fighting Championship is also in town. And so they're trying to figure out what they should do, whether they should go to the ballet or go to the fights. And here's the situation. Each one of them, of course, has the choice to go to the ballet or to the fights. And here are the benefits, the utility derived from each choice, each possible combination. If they both go to the ballet, Pat gets 2 units of utility and Chris gets 3. If they go to the fights, if they both go to the fights, Pat gets 3 units of utility, and Chris gets 2 units of utility. Now, if Pat goes to the ballet and Chris goes to the fights, they each get 0 units of happiness. And if Pat goes to the fights and Chris goes to the ballet, then they each get 1 unit of happiness. So we're using our game theory setup with the payoff matrix, and in this case the payoffs are in terms of utility. So what does this young couple do? Where do they go? What's our equilibrium under these circumstances? 1-1? Ballet or the fights? Both of them go. So you're liking both of these 2 solutions. So as we saw last time, remember we liked the solution of 50-50 with Coke and Pepsi. Both of them were better off, but yet we deduced that they didn't get that optimal solution. So that's kind of the things we need to grapple with here is, are we going to get to what seems to be the best here with both going to something? The question remains, which one? All right, so when you see these games on the final exam coming up next week, I suggest that you first check out to see if there's a dominant strategy. That's a good way to see if there's a quick solution to the game. So what was a dominant strategy? Who's got dominant strategy down? Good. So a choice that leaves a person better off no matter what the other person chooses is essentially what it's saying. So does Pat have a dominant strategy? Does Pat have a dominant strategy? No. All right, so let's go through the logic of how we did last time. So what we're kind of asking ourselves is there a dominant strategy for Pat? Question mark. And to do that, you take the other agent's choices and you say, okay, if Chris chooses the ballet, then Pat should choose what? So let you catch up with this. And again, we're kind of using the language of economics here. It's a little deciphering thing. If Chris chooses the ballet, then Pat should choose what? Ballet. Okay, so if Chris chooses the ballet, then Pat should choose the ballet because 2 is greater than 1. Okay? So then Pat should choose the ballet. 2 is greater than 1. Then we ask ourselves the other question, what if Chris does the other thing? If Chris chooses the fights, then Pat should choose the fights. Dominant strategy? No. There's no dominant strategy. So check it out. If Chris chooses to go to the fights, then Pat's better off with going to the fights because 3 is greater than 0. All right, so because we got different answers here, in one situation, go to the ballet, in another situation, go to the fights, there's no dominant strategy. Therefore, no dominant strategy for Pat. All right, so it was a good try, but it was unsuccessful in kind of helping us along with the game. Now, I'm not going to write it down. You guys can if you want, but does Chris have a dominant strategy? So for Chris, if Pat chooses the fights, what should Chris do? The fights, because 2 is greater than 1. If Pat chooses the ballet, what should Chris do? The ballet. No dominant strategy. So neither player has a dominant strategy in this case. All right. Where do you think they're going to go? Who likes what? Who likes what? If these are utilities here, who's the fight liker? Pat, right? So they go to something together. Pat gets a little more satisfaction than Chris, but if they go to the ballet, Chris gets a little more satisfaction. We can also see that here with the 0s compared to the 1s. So if they go separately to events, at least they get a little bit of happiness, although the star-crossed lovers would much prefer to be together rather than apart. But they at least would get some satisfaction if Pat goes to the fights and Chris goes to the ballet. All right. So where do we go, the fights or the ballet? Wherever the girl wants. So where are we going in this case then? The ballet. Who said there was a girl in here, Calvin? I didn't know if there was. Star-crossed lovers, yeah, but it's Pat and Chris. I was talking about a couple guys possibly here. Ballet or fights, or maybe this is a couple gals. So we don't want to bring those sexist thoughts into our minds that girls like ballet and guys like the fights. And so I don't know if I'm with you on that, if that's going to work, or I'll change it on you and say, suppose we've got 2 women or 2 guys. But maybe there's some cultural things going on there that in certain cultures the women might be the dominant one. I don't know. I'm not here to assess that, but that's Kellen's opinion. All right. Well, let's get back to equilibrium. We talked about Nash equilibrium. This is another way to kind of go about finding the solution. Are there any Nash equilibrium? So to figure out a Nash equilibrium, you can just pick a solution and see if it's stable or not. So if we pick 1, 1 here, with a Nash equilibrium, you want to say to yourself, would either party want to switch, taking as given what the other one's doing? So would Pat like to switch if he or she could? Would they like to switch their answer? If we're at fight and ballet 1, 1, would Pat like to switch if they could? Yes, because 2 is greater than 1. So it's not a Nash equilibrium. So up here, we know 2 is greater than 1. Pat wouldn't want to switch. Would Chris want to switch? No, because 3 is greater than 0. We found ourselves in Nash equilibrium. So, is Kellen right? We go to the ballet. we said that this one's a pretty good solution too, potentially. Shane identified that going together seems to matter. Is this one a Nash equilibrium? Yeah. Would Chris want to switch? No, because 2 is greater than 1. Would Pat want to switch? No, because 3 is greater than 0. We've got another Nash equilibrium. So this is one thing that's different than our supply and demand framework, where we did this and we said, oh, there's equilibrium price and there's equilibrium quantity, and there was just one equilibrium where the two lines crossed. Now, with this strategic behavior, under this definition that John Nash put for us, there's potential multiple solutions, multiple equilibria. All right, so that's a Nash, that's a Nash. We're now still back to the question of how does the young couple determine where to go? So now let's allow a little more reality into our discussion. The answer from the economist standpoint, analyzing the numbers, kind of ends here and says, hey, there's two possible solutions. Either one of those are equilibrium situations. And so now we can start to maybe add a little more reality to it, as Kellen was starting to do. Where do we go? The ballet or the fights? How would you, if this is your significant other, and maybe you guys have had situations like this, how do you come to a resolution? Do you just stay home and say screw it? Or do you actually end up going to one of these events?
Whatever's cheaper.
Okay, whatever's cheaper. Good. I'm glad you brought that up. So, other factors. How would you weigh that in, Deidre? So if this is the utility, just give me a little gut feeling here on how you'd factor that in. Anybody want to help Deidre out? It's a good comment to make. Just kind of tell me a story of, oh, we ended up at the ballet because related to her comment on cheapness. Here's the utility. Just tell me where we end up.
You say you're, indifferent between the two, and the way you decided was the cheaper.
Okay, the cheaper solution, right? So if we had ballet tickets at $100 and Ultimate Fighting at $200, total package for 2 tickets or whatever, then my utility per dollar is actually higher. Now, I can take that into account and kind of wash it away by telling you that these already are in utility per dollar. Okay? So great comment and very true. And that's what we learned in chapter 9 on the marginal utility divided by the price. So what is the utility of the ballet, the happiness that the ballet brings us, divided by the price of the ballet? And that is going to alter our choices. But let's just say that this already has that into account. So this is $2 per unit, 2 units of satisfaction per dollar. All right, so good, Deidre. How else does this young couple figure out where they're going? Imagine yourself in this situation. Now we've equalized the dollar aspect. We're stuck again. Where do we go? How would you guys solve this? I'm not looking for game theory or what the economist says. I'm thinking back to you. You and your significant other. How do you figure it out?
Maybe how much time you have and how much time it's going to take to get there.
Okay, so time now. Another very good comment. We can take that into account, similar to what I did here. Taking the satisfaction per units of time, kind of like per dollar. So we could take that into account. Good comment. What else? I heard somebody else starting to talk. Okay, go to one and go to the other. So we can start to introduce some notions of fairness. So you get to pick tonight, I get to pick next week, right? So you have a repeated game, right? See how the nature of the game makes a difference on how what outcome we might come up with. So if it's a repeated game, that might play a role. But suppose this is a one-shot deal where the ballet is this guy that's never been to the United States and he's the most awesome ballet person around the world, and he's coming to Ottawa for one performance only. And the Ultimate Fighting Championship is the championship that's never going to happen again. It's a one-shot game. Where do we go? Ballet or the fights? So again, all great comments. Money, time. Maybe we can alternate. Where do we go tonight, though, for Saturday night when both of these events are in town and they're at the exact same time? Keep thinking.
And we're not looking at the numbers anymore?
We are looking at the numbers. We've equalized the money factor, the Deidre factor. We've equalized the Kellen factor, the time factor. And we've determined it's a one-shot deal. Where are we going? It's decision time. Okay, so some sort of compromise. Maybe there could be some negotiations is what it sounds like, right? So if I have to watch it on DVR as opposed to watching it live, there's going to have to be some compensating differential coming from my significant other. You guys can figure out what that compensating differential might need to be. All right? So that's a possibility. It might be up for negotiations, which kind of brings us back to Kellen's original point of one person is dominant in negotiations and we tend to do what's going to happen there. So maybe there's one dominant player. One solution we haven't stated that's kind of an important one that I think you guys would say is pretty fair. Go to the ballet, we go to the fights. Rather than bringing in side deals. What else could we do? What would be fair? Half and half. Now, you're getting close to something there, but that would totally, you'd still have to buy a full price ticket for each, right? So there's that kind of, but you're getting close on the half thing. What else might you do? I'll give you a hint. You might go to your purse if you're one of these two females here, or your pocket if you're one of the guys. Flip a coin. Flip a coin. Something so novel, so simple. Well, it turns out that that is an equilibrium. From the economic standpoint here, that is a way to come to a solution. The solution is not to go to the fights per se, not to go to the ballet per se, but the equilibrium solution is to allow a fair coin to determine which one. Giving, similar to what I said Kellen was touching on, a 50% shot at going to this one, a 50% shot of going to this one. You see how that's a little bit different? That in and of itself is an equilibrium solution. It's called a mixed strategy, and both these two might think that that's a decent way to come to resolution on which one they ultimately end up going to. All right, so we got two equilibrium. Okay, questions or comments on that? I want to put that last thing down here. So key point here is that there are two Nash equilibrium, and there is a mixed strategy equilibrium as well. There is one mixed strategy. I'll put that in quotes. That's kind of the econ term here. One mixed strategy equilibrium. And that is to use a randomization device, fancy word for a quarter maybe, a randomization device that puts a 50% shot of getting one, 50% shot of the other. So if you take a die, that could be your randomization device. And if it's 1 through 3, we go to the ballet. If it's 4 through 6, we go to the fights. Okay? So mixed strategy equilibrium is flip a coin. 50-50 shot at one or the other. Okay. This game is called the Battle of the Sexes, by the way. And yes, traditionally we did not bring in gender stuff. I think the original has a very male name to one and a very female name to the other, and the female name was associated with a female type event of the ballet. Yes, it was the women, but we try to break, this is 2012, people, we try to break those gender stereotypes, right? So, but if you look in the literature, this is called Battle of the Sexes. Okay. New game. Matching pennies. Matching pennies. All right, so here's how the game works. Number one, each player, 1 and 2, have a coin. So it could be a quarter, could be a silver dollar, what doesn't matter. Each player, 1 and player 2, have a coin. Let's call it a quarter. Two. Each player chooses head or tail. Each player chooses head or tail. And does not show the other player. Step number 3. On the count of 3, each player reveals the coin. On the count of 3, each player reveals the coin. And the last step here is if the coins match, each player has a head or each player has a tail. If the coins match, then player 1 wins. If they don't match, player 2 wins. Okay, I don't have any change on me. Who's got a couple quarters for some props? Couple nickels, that'll probably work. Let's just use the nickels. So I just want to make sure we're all crystal clear on how this works. So Shane, let me play with you here. All right, so go ahead and choose one or the other, and put it on the back of your hand and cover it up. And then we're just going to go reveal it at the same time. 1, 2, 3, go. They don't match. I have a head, he has a tail, which means player 2 wins, and I'm player 2. So I win. All right, so that's the game. Set this game up in a game theory framework. So now it's on you. I'm not going to feed it to you. You've got the rules of the game. Put it into a framework, and you can work with your neighbor if you want. And I'll give you about, a minute or two here. So you should be setting up the game. We've got player 1 and 2, the head or the tail, and then the payoff matrix. Okay, I'm going to give an extra credit point to anybody that's got the right answer, the first person. So come on up. I want to show everybody in the room, but if you think you're pretty good with your answer, then just bring me up your paper. I want to throw it up on the board and check it out. Who's got it? I don't care.
Not the same thing. So.
Yeah, that's fine. Bring it up. I'll give you both a point. Yeah, I just need one. And you don't, I guess you don't even both have to come up. But the main thing I'm trying to accomplish here is just putting it on the board. All right. So we got player 1, player 2. I like that. Looks like head or tail, that's their choices. And then you've got the wrong answer in the box, so no. Anybody else? Come on up. Get in the line here. First come, first serve. Let's see what Gene's got. Gene's got WL, LW, no, nice try though. Let's see here, let me get a little zoom going. Oh, come on baby.
Yours doesn't work, sorry.
Alright, so, maybe I shouldn't have did that. Oh, jeez, the technology's not quite, there we go. Oh, no. Thank you. Curtis.
We were close.
Okay. No. No. 3 and 0. 3 and 0. This one down here at the bottom?
Yeah.
Here's Daryl's. That's a big no. Anybody else? Bottom. That's a big no. All right, so I'm just going to tell you, Curtis was the closest. So Curtis gets an extra credit point for being close, but now he seems to be making it worse. But where was he? All right. Oh, I see what you're doing. You're kind of getting closer, but well, not really. So you had 1s where these 2s are, right? And that was actually closer. So where you were wrong is in the amount of the payoff. What are we playing for? How much? The coin. So I assume you're kind of doing 1 coin, right? But we've got a little more information to that. So really it's a quarter. So we've lost 25 cents. So if we insert negative 25 and positive 25, which is what you had, negative 1, 1. So you were, I mean, he basically had it, except for the value of the amount of the coin is the only little tweak that I'd like to see. So let's all put that version on the board on your answers. So you should be going plus 25, minus 25 all the way through. So most of you had like this type of setup, player 1, player 2, head, tail, and let's see, player 1 wins if they match. So on a match, player 1 gets the 25 cents. I'm going to put just 25 with the little cents here. So 25, player 2 loses 25. And if they match, if they're both tails, player 1 still wins. So it's 25, negative 25. But if they don't match, then player 2 is our winner. So player 1 loses, player 2 wins, and player 1 loses, player 2 wins. Okay, good job, Curtis. Okay, back to the old thing. How do we play the game? Dominant strategy? Is there a strategy you can pick that would be always the way to play? No, right? You don't want to play heads all the time. So if we were playing a repeated game, that might not be a good strategy. Nash Equilibrium. How many are there up here? 4? 2? So with Nash Equilibrium, just ask yourself, would anybody like to switch? So would player 1 want to switch? No, because 25 is greater than negative 25, but would player 2 like to switch? Yeah, not a Nash Equilibrium. How about this one? Would player 1 like to switch? Yeah, not a Nash Equilibrium. Would player 1 want to switch? No, but would player 2 like to switch? Yeah. There's no Nash Equilibrium. So we've got no Nash Equilibrium with this game, which is kind of a key feature to this setup. So what we're doing here is I'm bringing you through a few different games. How many did I say there are of that type of thing where one's higher, one's lower? 72. There's 72 combinations of that type of thing going on with these simple four-square game theory. So there's no Nash Equilibrium. Okay. So now it's maybe even more confusing. Is there an optimal way to play this game? And let's just say we're going to play it for a while. We're going to play it 100 times or maybe even indefinitely. You know, because this is what I think in 7th grade I used to play this at the lunchroom. We'd bring quarters and we'd basically play this game. That's why I like to go through it. Is there an optimal way to play it? You could have different strategies. So one strategy, in fact, Shane, let's play it a while, okay? Okay, we'll identify. What did I say I was? I was, they don't match. That's Russ here. So what does that mean? Player 2 wins. That's me. I'm player 2. Okay, so if they do match, Shane wins. All right, I've got a strategy in mind. Okay, 1, 2, 3, go. They match. Shane wins. I got heads. He's got heads. 1, 2, 3, go. They match. He wins. I had a head. 1, 2, 3, go. They match. There's a head. He wins. 1, 2, 3, go. They match. He wins. 1, 2, 3, go. Ah, they don't match. I finally win. Now, what was Shane's strategy? Actually, I've never had this come up before. What was Shane's strategy, apparently? Keep heads the whole time. Now, you just did in reverse what I normally do in class, by the way, for the last 15 years, which was kind of cool. I had to think on my feet here what I should do. So I was pretty sure he was doing that strategy, and so I switched it. Now, if we kept playing and he holds to that strategy, is he going to win a lot of money or lose a lot of money? Lose. So it's a bad strategy to play one thing all of the time. Now, would he have been better off if he rolled a die every time, and if it's a 1, he plays a tail, but if it's 2 through 6, he plays a head, just like he was doing? Would he be better off doing that if he randomized his strategy, but he did it in such a way that 2 through 6, he played a head just like what he was doing, but he's got at least one little chance of playing a tail. What do you think? Could I still take advantage of that strategy? Yeah, because I'd start to see that he seems to like heads apparently. He's playing heads all the time. So I'd start playing tails more times than not to exploit that. So again, it's a bad strategy for him to play a 1 out of 6 strategy or 5 out of 6 strategy of playing heads. So what is his optimal strategy to play? Mixed strategy. What would be better to do if I can start to pick up on a strategy where he's randomizing, but it's in such a way that it's 5/6 of the time he's playing one thing and only 1/6 of the time he's playing the other? What would be a better strategy? $50-50. Flip the coin. So the optimal strategy is to keep me guessing. If he plays any other randomization technique, I potentially, after playing it for a large number of times, could take advantage of that. So again, the optimal equilibrium strategy for this game for each player is to play randomly 50% of the time each side. That is the solution to the game. That is the optimal solution. So there's no Nash equilibrium, but again, as we saw with the other, there's a mixed strategy equilibrium. Mixed strategy equilibrium, and that would be to play 50-50 again. So, because I did 50-50 on both cases, I just want to highlight one thing to you. In this particular case, it's 50-50 because of the payoffs. So there are times where the optimal strategy is to play something 5/6 of the time and 1/6 of the time, and it depends on mathematical calculation that I'm going to spare you guys on the relative payoffs of playing each. So if you've got one particular thing that's going to pay off big time, like there's a really big prize for this solution, then you may want to play it differently than if they're always this equal payoff. The last thing I want to comment on this is the type of game it is. This is called a zero-sum game. I think maybe I've mentioned that before. You may have seen it in other classes or cases, but this is a zero-sum game. What does that mean? A zero-sum game. And if you think about Curtis's illustration of one of the payoffs, it basically tells the definition of why. Somebody put that into words. If you look at one solution, it kind of says why it's a zero-sum game.
They all add up to 0.
They all add up to 0. And then it means that one person's wins is another person's losses. Many times people have the perception that things are zero-sum. Unfortunately, economics is one of those places in a number of areas. We think that if we take $1 from the rich and we give it to the poor, it's a zero-sum game for the economy. But it's not, potentially. If I take $1 from the rich, I give it to the poor, we have this going on between the rich person and poor person, but not necessarily in terms of society's benefits, because we have that deadweight loss with taxes. So there's inefficiencies that can be caused to where that might lower welfare for others on the island, even if it's a dollar for dollar transfer here. It's not in a dynamic sense. It might be today, but it might not be in a dynamic sense over time. Okay, so that is game theory. Questions or comments? Oh, we don't want to take your dime. Thank you. All right. think we are going to move into our market failures. That was probably a pretty good segue into market failures. All right, a lot of the fun, if you guys haven't been having fun, even more fun awaits you if you go a little bit deeper into economics as we look at unique situations. In fact, I've been talking with Dr. Epp on doing an environmental economics class for an IDS course. So that might be a direction her and I head on looking, kind of combining some environmental issues and economic issues is one example. And actually, we're going to do that in this next section. So to start you off here, I just want to say that the free market, as much as I love it, does not always allocate resources in the most efficient way. So there are some cases where we don't get the results that we'd like to from the free market. So one example was monopoly. We saw the inefficiencies created by having that lack of competition. And we might need some government intervention government regulation or other intervention at times when the market isn't quite doing what we hoped it would do for whatever reasons those are. Now, unfortunately, governments don't always have the best answer either. We saw that with a possibility in our natural monopoly. So we also have government failure. So be careful that the government may not have the right answer. The case study we looked at with ethanol was probably a good example, where we were trying to chase alternative forms of energy, possibly in part to help the environment, but it turned out that making ethanol is more detrimental to the environment than making oil. So that process maybe wasn't working, and the subsidies that we're providing might have distorted the market more than it helped. Okay, so that's a possibility. But nonetheless, the free market might need the government at different points. We got to have that caveat that we got to be careful with what we introduce. And we call this market failure. So that's what the remaining material we're going to look at addresses, is situations where the market doesn't provide us the ideal solution. I've always thought that this word is a little too harsh. Can't remember if I've told you this story already, but maybe it's worth saying again. You know, most of the time, the market is a straight A student. Most of the time, the free market is a straight A student. But even our straight A student sometimes gets lured away to the party and didn't get the studying in that he or she normally likes to do, and they got a C on that particular project, which led to them getting a B for the course or something, right? So there's circumstances where the market doesn't perform as good as it should and might need some corrections of some sort. And so one of those situations that this next chapter looks at is an externality. So an externality is a cost or benefit borne by a third party, not directly related to a transaction. A cost or a benefit borne by a third party, not directly related to a transaction. Underlying third party. So if we have some pollution going on, it's not the buyer of the product, it's not the seller of the product, but there's some sort of cost or benefit by somebody downstream or somebody that's affected by the production or consumption of the good that is kind of innocent. That is an externality, and that causes problems. All right, we'll pick up there next time on Friday.
Did you ever get those